Okay, all right. So it is my great pleasure to introduce Professor Richard Easther, who is the chair of the Department of Physics in Auckland, and was previously a professor of physics in Yale University. And most notably, amongst his papers, he was third author on my first paper. So this is the thing that I know him from. So thank you very much for coming to visit us, and please take it away.
Cool. Thanks for inviting me. And it's particularly good to see that Simeon, that the experience of collaborating with me hasn't held you back, and that you've pitched up at Riverside. Congratulations.
Thank you.
What I wanted to do was to focus on the first part of the talk is really a survey of cosmology, and so it's a fairly light touch, and some of what I'm saying will be, or much of what I'm saying will be familiar to most people, but I want to present a slightly unusual, or what at least to people outside of the immediate field will be a slightly unusual chronology of the universe, and to focus on the parts of it that about which I think we know the least. And so it's a working hypothesis at best, or a confirmed, at minimum, or a confirmed fact for some of my colleagues, that the universe underwent a long period of quasi-exponential expansion known as inflation immediately after the Big Bang, that somehow at the end of that process, the universe thermalizes, so it becomes, contains lots of hot relativistic particles and thermal equilibrium with one another, and then sets the stage for the the sort of classic first 3 minutes Big Bang, and then through to astronomy and astrophysics. And it's really the middle stage that I want to focus on here, and explain why that's a large piece of territory, that it's largely unexplored, but also look at the things that it can tell us, and the way, and what those things can teach us. This actually involves a reasonable cast of characters in terms of current collaborators. I'm working with my own group at Auckland, but also collaborating with Jens Niemeyer and Göttingen in Germany. We have a grant to run a collaboration between New Zealand and Germany, and he was able to visit us this year before he couldn't. And likewise, I'm also collaborating actually with Nikhil Padmanabhan and his student Luna Zagarak, who is Nikhil's obviously a former colleague of mine at Yale. So the sort of classical problem, what we think of as astronomy and astrophysics, we go out, we look up into the sky, we seek to explain what we see there. This is the sort of classical way of thinking about the universe and what we do with it. We know, or we've come to know, that the visible universe is finite in volume. And so, you go out on a dark night, you look at the Milky Way, you're looking tens of thousands of light years potentially. We can see the Andromeda galaxy, which is a couple of million light years away from us. We can look out into the Hubble Deep Field, and then some of the objects that we're looking at will be at a redshift of greater than 5. And at that point, we're looking most of the way to the edge of the visible universe. And in fact, when we look at the microwave background, we're looking at what, to all intents and purposes, defines the edge of the universe, and the patch of space-time with which we can regard ourselves as being causally connected to. In other words, that the light from the microwave background has been in motion towards us for approximately 13.8 billion years, minus the 380,000 years that it takes for the universe to become transparent. So this volume of space represents, in some literal sense, everything that we can see. And if we wanted to think, in more poetic terms, this is really the edge of the sky. This is as far as we are able to get. So if we want to understand the universe on global scales, the first thing we have to obviously take into account is that the trajectories of photons that have traveled through the universe over a period of time during which the universe can grow by an appreciable amount The overall trajectory, the distance that those photons have traveled, is a combination of their individual motion through space, but also the fact that space-time itself has been expanding. So it's a little bit like, astronomers like to think in physical coordinates, cosmologists maybe more often in co-moving coordinates. And so what we're doing is we're looking at space as a racetrack that's been stretched while the race is taking place. So the runners are always will assume that they're fit and healthy, and I'm not overdoing it in the first little bit. So they're moving at a constant velocity with respect to the track. But as the finish line can potentially be receding into the distance if the track is expanding faster than they're covering ground, but also the start line, the place from where they've come, the distance that they've traveled since the beginning of the race, will have increased because the universe is expanding. And so if we try to make sense of that expansion, typically in cosmology, we define the scale factor, which is a function that shows up in the metric of the space-time that describes the expanding universe. And so this will be familiar to anyone who's studied any general relativity. This is the function that tells us how much the distance between any two representative points is changing as a function of time. So you always have to set some instant at which that is calibrated, at which the scale factor is equal to 1. But then once you know the scale factor and you ignore the fact that things have peculiar velocities, that means that they're moving, potentially moving in space at their own, then the distance between those objects, if they're well separated and not gravitationally bound to one another, will be given by all of those points in space will be given by the scale factor that changes as the universe expands. And so plots like this, which again, the sort of things that you would find in fact, you can find plots like this going back to the 1920s, although not with necessarily modern numbers. In some cases, the scale factor well, in all cases start at 0. In the sort of classic closed universe, this is a sort of plot that you would have shown in a cosmology class in the mid-90s before dark energy was discovered. In some cases, the scale factor reaches a maximum, recontracts. In other cases, there's a borderline between contraction and expansion, the so-called flat universe, where the amount of material in the universe happens to be just sitting on the dividing line between these two things. This point is a repeller, is a special point in phase space. So if you start off slightly to this side of it, the distance will grow. If you start off slightly to this side of it, eventually you'll recollapse. These are all the sort of standard, as I said, this conception of cosmology, in fact, goes back to the work of Friedman and Lemaitre, Roberts in the 1920s, and Robertson and Walker in the 1930s. The one additional complexity that we've added to this picture in terms of the present day universe is that we know that dark energy, in fact, will drive us back towards this line rather than away from it, because at the present day, the universe is expanding, and the expansion rate of the universe is actually growing as a function of time, meaning that in a universe that's full of gas or dust, we expect that the rate of expansion of the universe will be decelerating, that the first derivative of A is positive, but that the second derivative of A is negative. But in a universe that's full of dark energy, that situation has been reversed. So the question becomes, or the question can become, is how much expansion has the universe undergone since the Big Bang? And if you simply take the solutions to Einstein's equations at their word, the answer to that is that A of t starts at 0, and it's now a finite number. So clearly that the total amount of expansion has in some sense been infinite. But we know that that's unlikely to be strictly true, because we know that quantum mechanics tells us that there's a minimum length at which it makes sense to think of space-time as being a purely classical and therefore infinitely deformable entity. And so at the length that's known as the Planck scale, about 10 to the minus 35th of a meter, we believe that space-time breaks down into quantum foam. So it's not necessarily self-consistent to imagine a universe where you're probing it on physical length scales, or space-time on physical length scales that are smaller than 10 to the minus 35th of a meter. So what we can do is we can take the whole, the whole of the universe that we can see, past the Milky Way on a dark night, past the Hubble Deep Field galaxies out to the microwave background. We can account for the fact that the universe has expanded since the light from the microwave background set out towards us. And we can ask ourselves, how much has the length scale, that would be the radius of the visible universe from us to the edge of the sky, how much has that distance grown since the Big Bang? And it turns out that's actually a quantity that we can, not necessarily, some of the numbers that I'm seeing, the age of the universe is in some sense derived, or at least this particular number is derived from observations of the microwave background, but it's consistent with the age of the oldest stars that we see in the universe, which is derived independently of that. Add a couple of 100 million years for those for the first stars to turn on. But the age of the universe is about 13.8 billion years. Maybe, the third significant figure there is significant. Sometimes, with WMAP we saw 13.7, and then at some point it clicked to 13.8 as the data changed slightly. So that gives us one number that we can hang our hat on. The second thing we know is that tells us that the horizon scale today, naively, would be 13.8 times 10 to the 9 light years. But we multiply it by a factor of 3 to account for the expansion of the universe. And in order to get that factor of 3, we're first ignoring the presence of dark energy in the universe today. And secondly, we're making use of the Einstein equations, the solutions for a homogeneous expanding universe, where that factor of 3 gives us the particular scaling that we need to get in order to account for the expansion of the universe. So that's a distance of about 3.26 times 10 to the 26 meters. There's probably maybe a couple of too many, couple of extra significant figures in that result. That corresponds to about 2.3 times 10 to the 61 Planck lengths. So if we wanted to take the largest physical scale that's observable by us, and we wanted to shrink that to the point that it would have been at the length scale where it would have been quantum foam, then we can guess as a reasonable approximation that the universe is expanded by about a factor of 10 to the 60 between the Big Bang and the present day. It can, of course, expand by a lot more than that, and the extra space-time that you produce in that fashion, if you start the universe at a scale close to the Planck length, that corresponds to the regions of space that lie beyond our visible horizon and therefore are experimentally inaccessible to us. So in fact, the universe can be almost infinitely big. The 10 to the 60 there is very much a lower bound. But it gives us a sense of the minimal amount of expansion that has presumably taken place since the Big Bang, given sort of standard minimal assumptions about both quantum gravity and also about the expansion of the universe in a relativistic theory of gravity. If you were to throw in, complexities such as extra dimensions and, various interesting things that have gone on in the early universe, you could certainly change this number, but this is pretty much the natural result that one would expect. Oops, hang on a minute. So what that says is if the scale factor if the scale factor if today is T naught, then when the scale factor was 10 to the 60 times smaller, everything that we can see today is in subsets some Planckian. Or another way to say that is the last 60 decades of growth of the universe. That's all that we are able to see in some direct experimental sense. Anything beyond that corresponds to distances that are unobservable to us, thanks to simply the causal structure of space-time. So the other thing we can see at the moment is we can see the microwave background. And the microwave background has a temperature of 2.7 kelvins. So this was the surprise that that was had in the 1960s. That what appeared to be the receiver temperature of this instrument that had been developed in order to, in fact, look at early communication satellites, in the sense that it seemed that their telescope gave them the same result wherever they pointed it in the sky. So that seems reasonable to think that there's something fishy with your detector, not that there's something fishy with the sky. Eventually, we realized that the universe is in fact full of what's today microwave radiation, and that has a temperature of about 6 times 10 to the 4 minus 4 electron volts. So the CMB yesterday, the photons in the microwave background are redshifted as the universe expands. So as the universe grows larger, then the wavelength of a photon will change in proportion to the scale factor. So the temperature of a gas of photons, the peak frequency of those scales, or the temperature and the frequency are linearly related to one another. So we know that when the universe was 1,000 times smaller, for instance, that its temperature will have been 1,000 times higher. So that actually corresponds to the point at which the CMB becomes, or above that scale. We believe that the microwave background, the photons that existed in the universe at that point, the average photon has an energy of 0.6 electron volts, but the highest energy photons in the tail, in the bluest tail of the blackbody curve, they have enough energy to ionize hydrogen. In other words, 13.6 electron volts. And so I made this slightly facetious comment that the extra credit here is that the universe doesn't become transparent when the temperature of the universe drops below the typical ionization energy of hydrogen. It's actually much lower than that. And the reason that that works out that way is that there are roughly 1 billion times more photons in the universe than there are hydrogen atoms. And so it's only the tiniest tail of the blackbody spectrum that needs to be at an energy that's capable of ionizing hydrogen to keep the universe ionized through to the point where it becomes transparent. And given that number, we can work out that we expect that that's at a redshift of about 1,000, or when the universe was about 1,000 times smaller today than it is today. Or put another way, in fact, I think that the exact number, or the number that's inferred from observations, is actually 1,080. So again, a number that has more than one significant figure, which for even at my age, someone who's been, when I started in cosmology in the early 90s, there was reasonable debate as to whether Hubble's constant was 50 or 100. And so again, this is an example of something that's been measured, an aspect of the universe that's been measured with some precision. So the universe was 1,000 times smaller. That's 3 decades of growth. And remember, we need 60 decades. We've got 60 total decades to play with. Everything that's happened in the universe since it became transparent, since the microwave background was laid down, has happened in that last 3 decades of expansion. We can work back further than that. The universe was 1 billion times smaller. The temperature gets up to I got that right? Yeah, 1 million times smaller than the microwave background. So 1 billion times smaller than today. The temperature was on the order of an MeV. And it's at that point that nuclear reactions can occur in the early universe. So this is the phase of nuclear synthesis that happens in the first minutes after the Big Bang. We go back a bit further, 1 trillion times smaller, and now we're starting to get a little bit complex. In the sense that the total number of relativistic degrees of freedom in the universe is not necessarily constant. And so if we think about the density of a gas of radiation, we know that scales like T to the 4th, but we also know that that's multiplied by the effective number of degrees of freedom, which for photons is obviously just 2. But as you get above the threshold at which things, for instance, like pair productions of electrons and positrons becomes possible, also at the point at which the neutrinos couple to other parts of the universe, the number of degrees of freedom will change. On the other hand, the degrees of freedom changes the density linearly. The temperature changes it as the 4th power. So the total change in the number of degrees of freedom actually affects what we're saying just by the 1/4 power. So even if you have thousands of degrees of freedom, it's only going to change the expected temperature at a given density by maybe a factor of 10. So the universe is at a temperature roughly equivalent to the proton mass. It's 1 trillion times smaller than it is today. Electrons and positrons will be happily pair producing off one another in those circumstances. And obviously, if we shrink it again, another 1 trillion times smaller, another 1,000 times smaller, we're starting to get up to the kinds of energies at which you would expect the quark-hadron phase transition to take place. So each time we make the universe a factor of 10 smaller, we're also making the typical interactions that are taking place in the universe a factor of 10 higher. So the temperature at which we would expect particles to be interacting in this primordial soup. So quadrillion times smaller, we're now at a TeV, and so the energy in the universe has now at LHC scales. And at that point, as I said, there's a comment there that the total number of degrees of freedom changes, but it doesn't have a dramatic impact on this argument necessarily. So when the universe is 10 to the 15 times smaller than it is today, the typical interaction energies that we infer by looking at the temperature of the microwave background and working backwards, those have reached the kind of scales that we are probing at the LHC. And that is the rough borderline at which the terrestrial experimentation and particle physics gives out. And so we can assume, as a working assumption that, an energy is significantly below the TeV scale, we have a pretty good idea of what particle physics is up to. There are certainly theories of dark matter that have a lower energy, a dark matter particle that has a much lower mass than this, which may mean that there are sort of stealth couplings between the standard model and other parts of particle physics that are important at lower energies. But again, as a rough order of magnitude sketch, it's once the universe is a quadrillion times smaller today, or 10 to the 15 times smaller than it is today, the physics that applies on a moment-by-moment basis in the universe, the detailed nature of those interactions is something that we don't have good experimental control over as particle physicists. So the universe, on the other hand, hits the Planck temperature, which is again the sort of the upper end of where we think particle physics will make sense. When the scale factor, which is about 10 to the 19 GeV, when the scale factor is around 10 to the minus 30 times smaller than it is today, or in other words, where the scale of the universe is 10 to the 30 times bigger than the Planck length. So it's a little weird that particle physics is telling us that we don't understand, we've reached Planckian energies at a time when we're still 10 to the 30 times larger than Planckian lengths. And so this is not the way that the classic problems of cosmology that inflation was introduced to solve. This is not the way that these problems, or this is not the way that this problem is typically first encountered. But I think it is another manifestation of the kinds of conundrum that come up when we try to make sense of the universe that we observe in the context of a classic Friedman-Robertson-Walker universe that's full of either radiation, which is relativistic matter that has pressure, or dust, which is to say, rocks or galaxies, or cold material, which has no pressure. Both of those things, both of those cosmologies have problems that were purportedly solved by inflation. But I think this mismatch between the point at which the Planck temperature is reached in our universe and the point at which the Planck length is reached, again, is telling us that those two things are not happening at the same time. The other classical problem, and this is the result that puzzled people even when we thought that the universe was within a factor of 10 of being flat, whereas we know today that the density of the universe is within about 1% of the critical density that would define the difference between a universe that expands forever and a universe that recollapses, again, ignoring the presence of dark energy in the universe today. So again, once the dark energy kicks in, that tight correlation between a universe that expands forever and the density of the universe that's decoupled slightly. But up until a few billion years ago, that would certainly have been, if we were teaching a cosmology class 8 billion years ago, the dark energy would be largely ignorable, and those curves would have stood would be reliable things to teach our students. The universe is also very smooth, and so the microwave background, the picture that I showed is from Planck, the Planck mission, and what they've done in order to make that picture is they've first subtracted the constant 2.7 Kelvin. So what you're looking at is, it's like looking at the waves on top of a choppy sea. So there's a mild 1 meter swell running, but the sea itself is maybe a kilometer or more deep. So you're looking at just the variations from place to place. It's about less than 1 part in 1,000 or 1 part in 10,000. The variation in temperature from one side of the sky to the other. The other things that they've actually had to remove to do that are obviously any foreground that's associated with emission, and from our own galaxy or from parts of the universe that lie between us and the microwave background. And they've also, in fact, subtracted a dipole term that is much larger than the variation from the genuine variation in the microwave background from place to place. And the dipole term is associated with the peculiar velocity of the Milky Way and the Earth within the Milky Way relative to the microwave background. So this microwave background is smooth to within parts in 10 to the 5. But in a classical cosmology, parts of those different sides of the sky have never been able to interact with each other. So the photon from one side of the sky has just made it to us. A photon from the other side of the sky has just made it to us. But apparently, miraculously, those two regions of the universe that can communicate with us, but have not been able to communicate with each other, are managed to ensure that their temperature is consistent to within parts in 10 to the 5. So the second two of these problems are things that were well known, certainly in the 1970s. And these are the things that Alan Guth explained by introducing the inflation. Other people around the same time produced, did work that we now realize does the same thing in the same way, but this has been standard part of our understanding of cosmology for the last 40 years. And so the other challenge that wasn't originally stated when inflation was introduced is that if you have a mechanism that makes the universe smooth, then you also need a mechanism that makes the universe not exactly smooth. If we'd rendered the universe entirely featureless, so that the temperature was the same from one part to the other, as well as we could measure, then the challenge then would be to explain why it was that that galaxies formed, why it was that structure forms in the universe on the scale that it does. So if you have a solution that makes the universe smooth, then you've also got to be very careful not to overdo it, because if you make the universe completely smooth, then structure formation in the universe will not happen, or will happen on timescales that are exponentially longer than happen in our universe. So there you go. So the way that inflation is usually explained is by saying that the universe is full of something with negative pressure. And so that seems a little peculiar, because we've got something with negative pressure that the negative pressure is simply something that does work on its surroundings by contracting rather than expanding. So positive pressure is the bottle rocket that I showed previously, where you fill a soda bottle with some water, which acts as a propellant, some air. The air expands. It does work on the water. The water is ejected out of the back of the rocket, and the rocket flies into the sky. So the universe, when it's full of radiation, is full of material with positive pressure. And a universe that's full of radiation, its expansion actually decelerates more rapidly than a universe that's full of material with no pressure. And the way we understand this intuitively is that the pressure of that material is indeed driving the expansion of the universe to a greater extent than it would if you set the pressure to 0. But the expansion of the universe is, as the universe expands, the pressure decreases. And so therefore it becomes less effective. Once it's doubled the universe in size, the pressure has gone down, and that makes the universe less effective at the next doubling is going to be produced less effectively, because the pressure that assisted it earlier on is less able to drive that expansion. So a universe with positive pressure will expand in some sense faster than it would have done if you took, if you turned that pressure to 0. But its expansion is also going to decelerate more rapidly, because the pressure has gone down as a function of time, goes down as the universe expands. So the perverse situation that we get to is that a material with negative pressure, you might reasonably expect that the expansion of the universe would, if it's costing energy to expand the universe, you might think that that would slow down the expansion. But weirdly, if you think about if you think about space-time as something that has some elasticity, and again, this is a very hand-wavy picture of inflation. But if we think of space-time as something with some non-trivial elasticity, where we have to put energy into the universe to expand it. If that elasticity is maximized, the density, the energy that we put in to drive the expansion has some mass associated with it. And so a universe that's full of material that has negative pressure, and that negative pressure is maximized to as large as we can make it without getting issues with superluminal sound speeds, the density of the universe stays constant as the universe expands. So you take a spring, you stretch it, that spring now has more energy, has energy stored in it that it didn't have in its resting state. It weighs slightly more. In the case of a spring that's made out of atoms, then the change in mass is obviously going to be tiny. In the case of stretchy space-time full of dark energy, the energy that is associated with the stretching in some very loose sense has to make up has to keep the total density of the universe roughly constant. And then, even without solving Einstein's equations, it starts to make sense that the density of the universe, if it's roughly constant and the universe is doubled in size, then the next doubling is going to look pretty much like the last doubling, in the sense that the total density of the universe hasn't changed very much, and that's the one thing that we have to keep track of how the universe is expanding. So the perverse outcome is that while you would think that negative pressure would in some sense resist expansion, it actually, in a relativistic cosmology, has exactly the opposite effect. If we maximize the pressure in the universe in dimensionless units, where C is equal to 1, the pressure is equal to minus rho, the density, it turns out that that's exactly the condition we need for exponential expansion, for a universe that is entirely dominated by dark energy or by a cosmological constant. So these things, this is obviously something that Einstein was aware of. He introduced a cosmological constant that was actually negative relative to the dark energy that we have today. He was trying to prevent expansion rather than encourage it. And it was Alan Guth who fully drew attention to this, the ability of material with negative pressure to drive expansion in the early universe. And so where we get to is an inflation, this period of accelerated expansion in the early universe. The pressure at that point is close in some sense to maximally negative. If you have a pressure that is so negative that the energy density of the universe increases as it expands, you get what's known as a big rip solution that violates various constraints that you don't want to be violating in general relativity, although you can certainly write down the math. And that situation corresponds to the pressure being equal to minus rho in units where the speed of light is equal to 1. In that case, the density is roughly constant. You get a situation where you can expand the universe by a great deal without changing its internal composition by a great deal. And so it's this that closes that gap of 10 to the 30 between the point at which the universe looks like energies would want to reach the Planck energy, but the length, typical length scales in the universe are still 10 to the 30 times larger than the Planck scale. During this time, the particle content of the universe will decrease exponentially. So if we take, if we imagine a universe that's dominated by dark energy, the universe is expanding, not yet exactly exponentially, but the expansion of the universe today is accelerating. On the other hand, we're not making any new atoms. And so the actual density of the universe, if the universe didn't have galaxies that are able to hold themselves together against that expansion, eventually you would have something that was a universe that maybe only had one or two atoms per horizon volume. So this exponential expansion has to be driven by something that's associated with not necessarily the vacuum, but it has to be something that's associated with some continuous quantity. It can't be driven by discrete objects whose density is reduced by the expansion of the universe. The difference between inflation and the dark energy dominated period that we see today is that we know also that inflation must eventually end. If inflation doesn't end, the universe would still be inflating. We would be living in a universe that was potentially had a density of 10 to the 15 GeV to the fourth. And so the fact that inflation must end tells us that the stuff that fills the universe during the inflationary phase has to be something that has some additional dynamics to it. It can't be a pure cosmological constant. The dark energy, on the other hand, that is driving the accelerated expansion of the universe today at very different energy scales. There's no reason a priori why the density of the universe cannot be has not been driven towards a constant value. There's no observational requirement that the dark energy has any dynamics beyond being a cosmological constant. Although obviously that is something that we're hoping to test with the next generation of astrophysical experiments, ranging from things like the Large Synoptic Survey Telescope through to the next generation of CMB experiments and other surveys of structure in the universe. So, the inflation, on the other hand, is a kind of logical requirement. It has to be something that's like dark energy, but time dependent in some mild way. Dark energy itself today is something that could be entirely consistent with a cosmological constant. So where that gets us is that the early universe undergoes this period of exponential expansion. At the end of that expansion, it will be cold. It will be almost empty in the sense that it will be very dense. But if you were to take a particle counter into the early universe, you would see almost no free quanta, propagating quanta. And it's almost exponentially expanding. The universe has to thermalize. We know that the early universe was hot, thanks to the microwave background. Also, the nuclear synthesis that was first discussed by Gamow and others in the late 1940s. And also the fact that, and further evidence that the universe is thermalized is that we predict the presence of a neutrino background, and that the impact of the neutrino background on the formation of structure and the properties of the microwave background is something that's been observed experimentally. It turns out the neutrinos decouple from the rest of the universe before nuclear synthesis. So the sense in which we have a probe of the temperature of the universe is actually our highest temperature probe of the early universe is in fact coming from the neutrino background, which hasn't been observed directly, but has in its impact on the growth of structure in the universe has been observed, as opposed to nuclear synthesis, which is something that the classic first 3 minutes where most of the helium in the universe that we see today was produced. Okay, so a checklist for inflation is that the universe is roughly flat. It's almost exactly smooth. It's not exactly smooth. And so a year or two after inflation was proposed, it was also realized that quantum fluctuations during this phase do in fact, the exponential expansion wipes out any initial inhomogeneity in the universe, removes any initial population of particles. But the fact that the universe or the quantum mechanical fluctuations in the material that drive inflation actually lead to inflation progressing at a slightly different rate, just by a tiny fraction in different parts of the universe, those lay down the perturbations that we see potentially in the microwave background, and which will source the beginnings of structure formation, the origin of the initial seeds that will grow into galaxies and clusters of galaxies once they're able to collapse in the universe. I haven't talked about it, but polarization patterns that we see in the sky also provide additional confirmation to the idea that these perturbations existed in the universe before the CMB decoupled from the rest of, before the universe became transparent. And also we see correlations on scales that are larger than the causally connected volume of the universe at the time the microwave background was laid down. The perturbations are adiabatic in the sense that it seems that they're produced in a single fluid. We're not trading off the changes in the mixture of the universe from one place to another. The perturbations are Gaussian to parts in 10 to the 4. So the initial perturbations that seeded the universe are highly Gaussian. Again, that's a natural expectation from inflation. The two things that we don't know about inflation, and firstly, we have no idea as to why the universe would have inflated. If you look in the literature, someone made a list of inflationary models, and I think they got to about 500. So inflation in that sense is a little like dark matter, in that we have reasons to be optimistic that it happened or that it's present, but we also have an almost infinite number of models as to how inflation could have happened, or alternatively as to what dark matter might be, which really speaks to our profound ignorance as to exactly how we have to extend known particle physics to make it happen. The other thing that we don't know is that if the universe is dominated by material, or the very early universe is dominated by material that drives this quasi-exponential period of expansion, we also don't know how that material couples to the stuff that the universe is made out of today. And so the universe today is made out of, obviously out of atoms. Also, there's a significant quantity of dark matter. And so some process in the early universe has to turn the energy density that was locked into the inflation field or into that drove inflation. It has to turn that material into the stuff that we see today. And this process, in doing so, has to render the early universe thermalized, so that we can get the physics that we expect from the neutrino background and nuclear synthesis. The other big debate about inflation, and this is something that going back to the 1980s, it was widely expected that inflation would lay down a background of gravitational waves. And this is actually something that, whether or not that was something that inflation needed to do, was in fact the subject of Simeon's first paper as a student with myself and Haranya Peris. So this is actually something, what our expectations are for inflation are really boiled down to ideas about naturalness. And those, can provide a guide to what we expect the universe to do, but they don't necessarily provide a compelling argument. So I think it's fair to say that the idea that inflation would lead to a stochastic gravitational wave background that would be visible both in the polarization of the microwave background and also potentially in solar system scale experiments with LISA-like gravitational wave detectors. That was questioned in the 1990s on physical grounds, that it's in some ways harder to make an inflationary model that happens at sufficiently high energy scales. The amplitude of the gravitational wave background is a function of the inflationary energy scale. So there's been 2 decades worth of debate in the theoretical community as to whether inflation is required to produce gravitational waves, whether inflation could produce gravitational waves, or even from some people that in fact you have to tune inflationary models to get them to happen at high enough energies to produce a gravitational wave background. So it's this background that was obviously claimed. The detection of this background of gravitational waves through the polarization of the microwave background was something that was claimed to have been seen by the BICEP 2 experiment and famously turned out to be polarized dust inside of the Milky Way. So at the moment we have upper bounds on the amplitude of the signal that are actually substantially tighter than the amplitude of the signal that BICEP 2 would have thought that it detected. And those actually put quite significant constraints on the inflationary mechanism itself. Inflationary mechanisms that people were confidently talking about in the 1980s are things that are now probably obsolete, in the sense that they typically very simple models of inflation produce larger, or algebraically simple models of inflation, I guess I should say, produce a larger gravitational wave background. Most of those scenarios have been experimentally ruled out. So I just want to pause here for a second. Are there any questions? I've given this kind of lightning sketch of actually this is the constraints on specific sets of inflationary models, which are driven by data. So the data are these regions here. Different inflationary models, not getting into the details of what they are, correspond to different regions here. This is a particular scenario. This is another one. These rectangles correspond to scenarios that have more than one free parameter. And so you can see that in some cases, some scenarios are looking, this one here, or this limit here would look pretty unhealthy. Models that are living down in this region here. This is the amplitude of the gravitational wave background, and this is something that tells us something about the spectral properties of the primordial perturbations. So, any questions at this point? This is an overview of the sort of introduction to cosmology, presented in a somewhat in a somewhat different set of units from the ones that we may usually see it, but giving a sense of how it is that that we think we need this extra period of expansion in the early universe. In that case, so where this gets us is a sketch of the expanding universe that looks like this. So the universe has expanded by maybe 60 decades since the Planck scale to provide all of the space that we see. 30 or more of these decades happened during the inflationary phase. This sort of moves off the left-hand edge of the screen. It could easily be hundreds or thousands or millions of decades of expansion, but it has to be at least 30. The era of expansion in which the physics in the universe are typically happening at scales below the TeV scale, that corresponds to about 10 to the 15 decades worth of expansion. And in the middle, you have what is sometimes and somewhat confusingly called the Dark Ages, because that same terminology is used to describe the period after the CMB decouples from the rest of the universe and before the first stars light up, so that there are no photons being produced in the universe. And so this region in the middle between the inflationary phase and the point at which the TeV physics is below the TeV scale, it turns out that region corresponds to about half of the post-inflationary expansion of the universe, if we think of that being driven by physics that happens at the sort of typical energies that show up in inflationary scenarios, about densities of about 10 to the 15 GeV to the 4th. So that, in terms of time, the inflation takes maybe 10 to the minus 32 seconds to happen for half of the total expansion of the universe to take place. Again, thinking of this in the logarithmic sense. The middle phase, this dark age, takes, the universe is now 13 billion years old. And this phase here takes, or this last phase here, takes all of that 10 to the 13, all of that 13 billion years, minus about 10 to the minus 12 seconds. So in terms of the total lifetime of the universe, this whole region here is about 10 to the minus 12 seconds, but it's also about 3/4 of the growth of the universe. So it just so happens that, if the given where we think of as the boundary layer, the boundary of our ability to test particle physics experimentally, just neatly splits the post-inflationary growth of the universe and roughly in two roughly equal pieces. And it's only equal if we're thinking in terms of a clock that runs relative to the expansion of the universe, rather than a clock that's keeping that's ticking in terms of seconds. So the key thing about this phase is that all of what happens in here in terms of the physics is happening at energy scales beyond the reach of the LHC. So we obviously have tons of theoretical predictions as to what might happen in that space, but also very little knowledge or constraint. The complicated thing is that inflation itself, probably one of the reasons, if we're cynical about it, that so many papers have been written about inflation, is that it's actually relatively easy to specify and then analyze an inflationary model. That's something that that involves perturbative physics. Once the model has been specified, and usually a fairly clean set of predictions. On the other hand, as we're going to see in this phase here, it turns out that the universe is capable of producing incredibly complex dynamics, but that happen, that the physics that drives them is stuff that we can't test in other ways, and that whatever happens in that phase, with the exception of the production of dark matter or possible primordial black holes, whatever happens in that phase is necessarily evanescent, because it's going to be washed out as the universe thermalizes. So I just want to say this is not the regular dark age. So when people talk about probing the dark ages, they're often talking about making measurements of, for instance, the hydrogen 21 centimeter line at scales that at redshift of 10 or more, where you're actually probing the distribution of neutral hydrogen in the early universe. And when the first stars turn on, the UV flux from those stars reionizes the universe and makes reduces the amount of neutral hydrogen in the universe. So this is not the regular dark age. This is the dark age that's taking place, both because we don't understand the particle physics that applies, but also because we don't have a lot of well-developed experimental probes of that phase. And so what I want to do in this talk is or the second part of this talk, is to focus on something that's run through my own research and that of others over the last years, without me necessarily realizing that it was becoming a thing, which is to say, what constraints do we have on the behavior of the universe during this primordial dark age, and what observables do we have that might shed light on this? And also, does this give us a tool for using cosmology to test, theories of particle physics that operate at energies that are well beyond the range of terrestrial experimentation. So the first thing that I want to look at is not so much a constraint, because it depends on our assumptions about the inflationary dynamics. It turns out that the inflationary dynamics can be specified in simple models in terms of the potential of the so-called inflaton field. Now, in simple models of inflation, the inflaton is simply a single scalar field. In more complicated scenarios, it can be many other things, even scenarios where the accelerated expansion is driven by something other than a pure scalar field. But in simple models, and as I said, there are hundreds of them that have been written down, the inflationary scenario is specified by the functional form of a potential in which the inflaton moves. So the potential can have many different forms. This one here is a simple quadratic. This particular potential has been ruled out by observations of the microwave background and the absence of a stochastic gravitational wave background of the form that Bicep claimed to have seen. And so as inflation progresses, the inflaton has the same value, almost exactly the same value at every point in the universe, and it rolls slowly down this potential towards the origin. The expansion of the universe creates a friction that means that it doesn't roll quickly towards the origin of the potential. At some point, typically when the inflaton potential has become, or the inflaton field value has become less than the Planck scale, that friction becomes inefficient and the field will roll quickly towards the minimum and then undergo a period where it oscillates coherently. And so you have a universe that consists of a the many quanta of the scalar field that are coherently sloshing backwards and forwards in the bottom of this potential. In a simple inflationary model, the earlier you, the higher up the potential you go, obviously the more expansion will happen between this and the end of inflation. And so the model, the pieces of the potential that are responsible for determining the perturbations that we see in the sky, whether it's in the microwave background or in the early, or that seed the formation of structure, they'll typically be a patch somewhere up here. And by looking at the power spectrum of those perturbations, we can relate that to the properties of the potential, both its slope, but also its second, and with better observations, potentially its third derivative. So we know that in simple models of inflation, the potential has changed by a factor of up to 100, or the value of the potential during between the point at which the astrophysical perturbations would be laid down and the point at which inflation comes to an end. In order to evade constraints that come from the absence of a gravitational wave background, we actually need a potential that is somewhat flatter than quadratic. So a potential that, even if we assume that it has, that it's well defined by the first term of its Taylor expansion at its minimum, which is not an unreasonable thing to do, then we know that the potential has to open out at a rate that is less than purely quadratic, that we need a somewhat concave inflationary potential. That's not something that we knew arguably 10 years ago. It is something that that is strongly suggested by the data today, if we assume that inflation is the mechanism that solves these cosmological conundrums. So it's easy to have a relatively standard minimum and also a flatter potential, but you can also imagine scenarios where the mass that's defined by the second derivative, the mass of a particle, a scalar particle, is the second derivative of its potential to a first approximation, rather than the mass squared. And so you can imagine scenarios where the mass is defined by the kind of mass that we would need to drive quadratic inflation. You can also get more complicated scenarios like this, where the mass at the origin would be quite different from the second derivative out here. So the classic picture of inflation that that this goes back to about 1982. So it's not the version that was introduced by Guth, because his version of inflation solved the problem of explaining how inflation ends by actually not having inflation end at all, at least globally. But the so-called slow roll inflation, which was developed by Albrecht and Steinhardt and by Andre Linde, that involved a field that was slowly moving, so that keeps the density of the universe almost, but not exactly constant, drives the accelerated expansion we were talking about, and in at some point that that the field point picks up speed, consistent with the damping that comes from the expansion of the universe becoming less effective, and then makes this moves into this oscillatory phase as the field point oscillates about this this minimum. It turns out that the thermalization history of the universe is
about 5 minutes. If it's, you've got maybe 5 minutes.
Oh, it's truth. I've completely missed my. Okay, sorry.
Sorry.
Okay. So the thermalization. So let me move through more quickly to this. I didn't have a clock running, so I haven't been able to see the time. A thousand apologies. Way too much introductory material. So it turns out that this uncertainty here is related. So the uncertainty in the predictions of inflationary models are related to the integrated behavior of the universe during this this dark age. So given an inflationary model and a theory of, if we knew what the inflationary model was, then we would be able to constrain the growth of the universe. The second thing that can happen is that thermalization can happen very quickly, or it can happen very slowly. The slow mechanism of reheating was something again proposed in the 80s. The fast mechanism was that the oscillating field can parametrically produce quanta of fields that are coupled to the inflaton. This was something that was proposed in the early 1990s. Go through. Actually, this is going to work out okay. So in the case where parametric resonance is supported, or this resonant growth is supported, you can very quickly establish thermalization, maybe in the first factor of 10 of growth of the inflaton after the end of inflation. It's not guaranteed. Whether or not you get that depends on the way that the inflaton couples to stuff outside of the inflaton field itself. So that depends on the nature of the theory, and because we don't know what drives inflation, because we don't know how physics works at energies above the TeV scale, all of these things on the one hand are free to be specified by the modeler, on the other hand are things that we don't have a good handle on. What resonance does is that this one on the right is the inflaton field. I've normalized it, so this is a flat spatial slice. And what we're going to see is this is a field that's coupled to the inflaton. And you can see that eventually the exponential growth of the inflaton field of the perturbations here drives the production of quanta in this field, which then backreacts on the inflaton and renders the early universe full of quanta, not necessarily thermalized, but quanta that can interact with each other and become thermalized. And so all I've had to do to make this happen is to add this extra coupling to the inflaton field. I'll skip past this. You can actually form persistent structures in the post-inflationary universe that are supported by the kind of intrinsic Klein-Gordon dynamics, these so-called oscillons, which would be long-lived and would give you a phase in which the universe has these long-lived stable structures that are held together by the nonlinear dynamics of the inflaton field itself. The plot here shows a region of constant density. And so you can see that this is again driven by nonlinear dynamics in the early universe. The things to take away from this are that while the inflationary universe is very smooth, and I'm sorry about messing up the ratio of the first half and the second half of my talk here. While the early universe is very smooth, the post-inflationary universe is both subject to nonlinear dynamics, to the point that the universe can easily generate a significant gravitational wave background. And so this is happening because the material in the universe is being accelerated at every point. This is a classically driven gravitational wave background, very similar to what we would see potentially from a first order phase transition at the electroweak scale. The potential downside of this background is that you're seeing that it's at scales that are potentially getting up towards a gigahertz in terms of frequency, so much higher than the kinds of scales that we would see at LIGO. So as I said, I'll just throw out this. I would love to talk to AMO people about the possibility of tabletop gravitational wave experiments looking for this potential signal coming from these relatively generic post-inflationary resonance, which can drive the production of particles in the early universe, which can lead to a significant gravitational wave background, but one that's hard to detect in the sense that most present-day gravitational wave detectors have been tuned to expected astrophysical sources. We don't know how generic resonance is. And it's not the same as reheating because it doesn't thermalize the universe and it doesn't necessarily produce standard model particles. The thing that I've been focusing on for the last couple of days, the last couple of years, is what happens if we don't have resonance? And so then reheating has to proceed perturbatively. This is something that I first looked at with Raphael Flauger and student James Gilmore 10 years ago. And the basic idea is that the post-inflationary coherent oscillations produce a universe that behaves as if it's matter dominated, that if it has no pressure. Perturbations in that universe grow linearly with the scale factor. So once you get to an energy scale of about 10 to the 10 or 10 to 11 GeV if you've started at the gut scale, which is where we think inflation happened. The universe, the post-inflationary condensate will in fact be fragmented by its own gravitation, the growth of gravitational perturbations. This is something that has been a possibility since these models were first proposed in 1982. And it's only in the last year that we figured out how to model the the nonlinear growth of this class of perturbation. So rather than the nonlinear dynamics being driven through the nonlinear terms in the inflaton potential, in this case, it's being driven by Newtonian gravity. So we're seeing something that's almost exactly analogous to the collapse of structure and the growth of structure in the universe after the microwave background decoupled. So in this case, the confining potential is coming from the Newtonian gravitational potential of of the overdensities that are growing. So we couldn't solve the Klein-Gordon equation to do this, but that would mean resolving the oscillation scale, which is thousands of times shorter than the scale on which structure is growing once the universe gets underway. So this is a problem that essentially has two clocks. It's got one which is set by the mass of the field, and it's also got one which is set by the Hubble time. Those things are initially similar to each other as inflation ends. As the universe grows by a factor of 10 to the 5, they become dramatically decoupled. And so it would be computationally infeasible to watch the gravitational collapse of these scenarios. It turns out, though, that this scenario, that where you have quantum matter that obeys Newtonian gravity, is described by something called the Schrödinger-Poisson equation, where the potential is coming just from the classical gravitational potential of the stuff that the density is proportional to the wave function squared. And it also so happens by a happy coincidence that my group had been thinking a lot about ultralight dark matter, which is exactly a quantum condensate that is gravitationally confined. So we had a solver for the Schrödinger-Poisson equation. We solved these equations, or we took the solver that we already had and we adapted it to the post-inflationary universe in scenarios that didn't undergo resonance. We added expansion, which is not too hard. We checked the conditions for validity for the Schrödinger-Poisson equation applied, which it turns out that it did, which is good. And what we saw is that we were able to evolve the universe into the point where this classical smooth condensate has been gravitationally disrupted. And so these lines here correspond to perturbation theory, and these lines here correspond to our simulation. We terminated the simulation at the point at which we became unable to resolve the velocities, which for complicated reasons to do with the Schrödinger equation, to do with the gradient of the phase of the wave function between successive points. We were using a fixed resolution, so we didn't have an AMR code. With an AMR code, we'd be able to follow this for much longer. We wind up with the post-inflationary universe picking up over densities in the inflaton field at scales that are much, much smaller than present-day astrophysical scales. These white regions here correspond to over densities that are greater than 100. Likewise, because this is really looks like collapse in a matter-dominated universe, we also start to see the beginnings of something that looks like a cosmic web, but again, that's forming in this primordial dark age, and with these occasional knots of material that are 100 times or more than 100 times denser than the background. So this is a proof of concept that we can now, for the first time in 40 years, solve. Ironically, while the dynamics of resonance are more complicated, it also happens more quickly and on timescales that are more easily evolved. Basically, what this does is the kind of WKB approximation where we take out the fastest timescale. We're actually working on codes for solving ultralight dark matter behavior, axionics, something we're almost finished. I also have a code that have been developed with people at Yale that is designed to run optimally on large distributed computing environments. Then we've got up to 4,096 cubed. And so this work came out in PRL just a month or so ago, a couple of months ago. And the nice picture, the easiest part of the job was making the picture. And of course, that was the part that, that the editors of PRL liked the best. So the consequences of this is that you can form, have a phase in the early universe where you form things that are analogous to axion mini clusters or boson stars, where we can see the central density of these clusters get up to about 10 to the 67 kilogram meters cubed. But still, it turns out in a regime that is safely Newtonian, the curvature of space-time isn't getting close to the point where we'd worry about the formation of black holes. And so we can form these kind of clusters of inflatons. If the inflaton, is producing matter by pairwise interactions, then a reheating of the universe is going to be happening in this highly overdense scenario rather than happening off this, coherently oscillating condensate. We don't know what the implications of that are, whether the inflaton decays or annihilates. We're hoping that we will be able to say something relatively generic about the kinds of pathways to thermalization that must be supported by inflationary theories that don't support resonance relative to those that do, which allow us to say something generic about the reheating of the post-inflationary universe in ways that have not currently been possible. Also, just in a final point, we were able to adopt the Preschecter formalism, which is used to describe structure formation, sort of at galaxies. We can also apply this equally well in this phase in the early universe work that I did with Jens. So where this gets us to, just summing up at this point.
I must ask you to.
Yep. Is that in the modern universe, nonlinear structure formation happens in the last couple of decades, the last 100, while the universe has grown by 100 times. In the Primordial Dark Age, the condensate fragments about 8 decades in after the end of inflation, but you have another 7 decades between that and the point at which you have to thermalize. We can see complex and unexplored nonlinear dynamics. It's also going to change the way that we think about the production of dark matter in these scenarios and the origins of baryogenesis, but we're also well out of thermal equilibrium during this time. All of these structures must eventually melt because we know that the universe thermalizes, so we can't have cold gravitationally bound structures, but there's lots of thoughts that are going on. The last thoughts are that even the simplest inflationary models can have complex dynamics. And so we might worry as cosmologists that we spend too much time building models and not enough time exploring their consequences. I'll leave it there and I'll take questions. I'm really sorry for running over time. I realize this is the first time I've given a talk where I didn't have a clock that I could see, and I put this together from as you can tell, it's not a talk that I've given previously. So so 1,000 apologies. I'll have to rethink the delivery of this, but happy to take questions at any time that's left.
That's all right. Thank you very much for coming to visit us. I know it's a little difficult to time it over Zoom, but I'm sure the introductory material was very interesting. Any questions? Any questions? Come on. I have a question. So could you say a little more about these tabletop gravitational wave detectors that you were talking about?
So this is something, goes back to work that I and others did about getting on for a dozen years ago now, is that we know that if inflation undergoes, or the universe undergoes resonance at the end of inflation, that, that is something like, it's an explosive production of particles, and you have all of the material in the universe is being violently accelerated. And it's doing it at a time, so it's doing that at a level that will produce a detectable gravitational wave background. The total energy density in gravitational waves at the end of that process can be 10 to the minus 7, 10 to the minus 6. That's diluted, by the fact that the subsequent, the universe goes through a matter-dominated phase. So, you get down to about 10 to the minus 10 in the present day. But that leads to a stochastic background that when you map the wavelengths of those gravitational waves, taking into account the expected amount of expansion, puts them well above LIGO scales and for most inflationary scenarios. And so no one has most of the scenarios that people think of, partly interferometers work better at lower frequencies for stochastic backgrounds. So it's much easier to build SIGO or LISA than it is to go after these backgrounds. But also there's really been no theoretical guidance as to what the expected signals might be. And so if you had an idea that would be sensitive to a stochastic background of gravitational waves, which is much more likely to be, cold atoms rather than, a laser-based interferometer that would operate at those energies, then at least there's the possibility that, there's a large number of astrophysical theories that are required to produce those backgrounds. The amplitude is obviously a function of theoretical parameters, so it's a relatively poorly constrained theory space, but there's certainly a possibility if you were to build something that was sensitive. It's a hugely complex task when you actually go and look at the kind of sensitivities that you need for stochastic backgrounds at that frequency, but it's at least something that's a possibility, and so it's something that I like to throw out when I talk about these theories.
Any more questions?
Hey, yeah, I have a question, Simeon.
Go ahead, please.
So Richard, this is Anson. So it's good to see you. It's been a long time.
You too. Yeah.
I was wondering if you could say a few words about the alternative model that Paul Steinhardt and others have advocated. What is the status of that? Have they been essentially ruled out at this point, or are they still?
Do you mean the ekpyrotic model, this kind of brain collision? Because they've had a couple. Yeah, it's tricky. It really boils down to. There's a lot of sociology about this. I think Paul would argue, or some people would argue that the community kind of clustered around inflation too quickly and now doesn't want to move. I think there's probably some truth to that. On the other hand, the model that Paul proposed originally had predicted a level of primordial non-Gaussianity, which is ruled out by experiment. And so Paul, tweaked, the parameters were tweaked to make it consistent with observation. And so initially that was the non-Gaussianity was described as something that was sort of an up or down test. And in some ways, but inflation committed the same sin in some sense, and that the gravitational wave background was widely described as a smoking gun. And I guess that's probably true. If you had seen the gravitational wave background that Bicep 2 was talking about, you'd have to work quite hard to think of what else it might be. But I guess most crime scenes, the perpetrator doesn't leave a smoking gun behind them to find. And so, we might be making inferences from, much more indirect and kind of circumstantial results. Paul argues in particular that that inflation should be expected. This is exactly the question that Simeon and Haranya and I looked at, that it's kind of natural for inflation to produce a large gravitational wave background. And I think the truth is more complicated than that. But if Paul was correct in establishing that point, then the non-observance of the gravitational wave background would be making inflation look sick. But I think the kinds of constraints that come from particle physics, particularly around protecting the inflaton potential against kind of Planckian corrections, which you expect to be there generically from effective field theory, they actually push you in the direction of a smaller gravitational wave background. And so it's really not clear what inferences we should draw about inflation as a concept from the fact that we haven't seen a gravitational wave background, although it certainly rules out particular models of inflation. Paul, if Paul was giving this talk, he would say somewhat different things from me. But it's clear that something has to. Ultimately, what inflation does is it decouples the physical size of the horizon. It says that there was a moment where the piece of space that we could see was getting smaller in the early universe, and Paul's models do that in exactly the same way. Not in exactly the same way, but they have exactly the same impact. So I think the generic idea that there has to be a period of what looks like expansion in the early universe is true, but in Paul's case, that actually turns out to be a period of contraction, in some previous phase, or something that is in some sense dual to that. So I'm trying to be as I'm trying to be as charitable as possible. I personally don't find Paul's model particularly compelling, but I think we do. The same argument probably goes for expectations around TV scale physics. If you'd taken a bet in 2010 at what the LHC was going to see, I think not many people would have said nothing. And I think we have to be aware that some of this is determined by taste, and what other people in the field are working on is what looks exciting. And so there's always the possibility that we could have some radical misunderstanding or lack of insight, and there's some additional kind of piece of the jigsaw puzzle that will change our picture of the early universe. Does that make sense?
Yeah. Yes, thank you.
All right, thank you. Any more questions? It's 5 o'clock, which is normally our time for being thrown out of the extra auditorium. So,
sorry.
But that's all right. So thank you again very much for coming to talk to us.
Thank you for having me, and sorry for abusing your hospitality.
Right.
Okay, take care.
All right, thank you. Bye-bye now.
Yeah.